is that stuff where y prime is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. Remember that? Okay, so there's going to be one of them, guaranteed, and it's going to be worth about how many points? About 10 points, which is good news because that's one whole letter grade that you already know about, isn't it? Okay, so you can prepare for that, and we've talked about how to prepare for that. It'll very likely be some type of a quadratic. So for example, it'll be something like y equals 3x squared minus 5x plus 17. Now everybody here knows the derivative of that. What is it? 6x minus 5, isn't it? Okay. And in the question, I'm just going to flat out tell you the derivative is 6x minus 5, and I'm going to ask you to prove it. So being able to write down that the derivative is 6x minus 5 isn't going to get you any points because that's going to be part of the question. Explaining to me that you take the exponent, drop it out front times whatever the coefficient is, and then subtracting 1, how many points is that going to be worth on this question? That'll zippo, because that's not using the definition. Does that make sense? Be careful, that's using the power rule, which is a completely legit way and the normal way we're going to do derivatives. Okay? That's how we're normally going to do them. But I want you to be aware of how this definition of a derivative works. Practice a number of these before Friday so that you don't wind up spending 40 minutes of your time on that problem. What's the issue with spending 40 minutes of your time on this one problem? That gives you 15 minutes to do the rest of the test, doesn't it? That's kind of slim on the time. The cool thing about this question, though, is you know it's coming. You know how to make up example problems. You can practice them all day long tomorrow and get this down to the point where you just flat out fly through it. And you know that you're going to walk away with 10 points right off the start of the test. Okay? So be aware that that's there. And it's going to be worth right around 10 points. The test will be about 4 pages. Of course, there'll be spacing to work out the problems in between. It'll be about 10 questions. So it'll be something like that. Okay? So what's going to wind up happening is we're going to have this review section stuff. Section 1.1, definition of the derivative. Then we started getting into right around 1.3. I think 1.2 was the definition of the derivative stuff, if I remember correctly. Okay, yeah, that was starting to get into it. We were talking about continuity there. What does continuity mean? Continuity. One of the things that's very important is to be able to ascertain whether a function is continuous. Well, the easy way to say it is you can draw the graph without ever picking up your pen or pencil. There are no breaks in it. Okay? So the easy way is to say, hey, you can just do whatever. It's continuous. It doesn't have any breaks in it. But there's a more formal way to describe that, because if you're on a computer or something and trying to get the computer to do this stuff, you have to be able to put it in machine language or be more specific other than just don't pick up the pencils. Is the computer going to be able to make much sense of that? Not really. Okay. What continuity really means, and we're going to get a little bit more particular, continuity at a point, at one location, because it's entirely possible for a graph to have a break in it. But if we're not working close to that break, the break isn't any problem at all to us. Okay? I mentioned a couple of minutes ago, Montana got how much snow in some places? 3 feet. Is that a problem for us? No, because it's pretty far away from where you're driving. Okay? So the idea of continuity at a point looks at, if you have a graph, and it does something like this, and here's x equals 5, is this function continuous at x equals 5? The answer is nope, it's not. We can all see that, can't we? It has a break in it. But how do you explain that it has a break in it? Well, some of the things that you have to be able to do are, first off, say that the limit as x approaches whatever value you're interested in from the left and from the right is going to the same place. And that's where this one breaks down. This one does not work at 5 because if we're coming in from the left, let's put some y values in here. Let's say this is 4 and this is 1. If we're coming in from the left, traveling on that function, as you come in from the left, where does it look like you're headed y value? What y value are you headed to? Does it make sense that it's 4? Okay, so this limit is going to have a value of 4. If, that's not exactly what I really wanted, if we head in from the right, what y value are we approaching? Notice I didn't say what y value do we get to. What y value does it look like we're driving toward? Looks like we're headed to 1, doesn't it? Okay. I know we don't actually get to 1, but it looks like that's where we're headed, and that's all the question asks is where are you headed. So the first criteria that needs to be met for it to be continuous at a point is if you come from the left or you come from the right, it looks like you're headed to the same place. That doesn't mean that's where you're going to wind up. It just says it looks like you're headed there. Okay? Then, the second part to this is that at x equals a, f of x equals f of a. You get to whatever that specific y value is. Now, you got to be careful here because it's entirely possible that this function may actually go like this, and up here at 8 is where you land when x equals 5. Does that make sense? So it could be that actually the function's value is 8 when x equals 5, which is a completely different location from either direction, isn't it? Now, neither direction looks like it's headed to where you actually land. The third thing that has to work is the limit as x approaches a. Remember now, this limit means from the left and the right at the same time, doesn't it? Okay. Equals f of a. Which means that if I'm coming in from the left, it looks like I'm headed to a specific y value. If I'm coming in from the right, it has to look like I'm headed to that same value, and when I really get there, that's where I am. Okay? This function is definitely not continuous at x equals 5. However, if we take a look at something like x equals, let's say -2. Is the function continuous at x equals -2? if you come in from the left, I'm not sure what that value is. Let's make something up. As you come in from the left, it looks like you're headed to a y value of what? 3. As you come in from the right, it looks like you're headed to a y value of 3. So that takes care of this first part. If you come in from the left or the right, you're headed to the same number. The second part says at a, well in this case it would be a -2, you come into a particular value. Yep. And, okay, important, this exists. Okay, this is what this really means here. You may be thinking, well, that seems kind of obvious. It may not always be the case that the point exists. For example, suppose over here at x equals 5, I erase that red dot. Is there now a value at x equals 5? No, so number 2 would not be met, would it? It would fail. Okay? So it's possible that things don't always work out. But in this second location, x equals -2, come in from the left and the right, yep, looks like we're headed to y equals 3. If I look at the actual function, hey look, it does exist. When x is -2, we get a y value of 3. And then the last thing, well, let's see, this limit, in this case, goes to 3. The function has a value of 3. So where it looks like it's going is where you really end up. Does that make sense? Okay. If you're asked to prove continuity at a point, and this is going to be really important, we can't do a derivative if we don't have continuity at the point that we're interested in. And since the whole semester is all about derivatives, being able to prove continuity at a point is probably kind of important, isn't it? Because the derivative doesn't exist if it's not continuous. Maybe this is going to be kind of important down the road. Hint. Okay. Does it make sense how to show that something's continuous? You got to do 3 things. Show the limit from the left equals the limit from the right. Second, show that at that specific point you're interested in, for example, x equals 5, show that it really does have a value. As the graph stands right now, does it exist at x equals 5? No. And if that happens, that doesn't mean it's bad. It doesn't mean you've done something wrong. All it means is, hey, it isn't defined there. It's not continuous there. I'm done. And you can say it just like that. At x equals 5, the function is not defined. It doesn't have any y value. So it's not continuous. If you have it existing, it's defined. If you have the limit existing, you go down to the third part. Do the 2 things that we just did equal each other? If they don't, you're done. It's not continuous. That's how this third step here is important. Okay. That's a big indicator whether you can draw this without lifting the pencil. You actually end up where it looks like you're heading. That means we didn't have to lift the pencil. Okay. Maybe take note of that. That's section 1.2. May want to take a look at some of those in the book, in the homework. Okay. In section 1.2, here you go. Okay, on page 125 and 126 of the book. Starting with number, well, it goes all the way back to 59, even earlier than that. There are a whole bunch of them here to talk about continuity. It starts at 52. From 52 all the way over to 82. Holy mackerel, that's 30 problems. From 52 to 82 in the homework. Okay, and that starts on page 124. Those are all problems that ask you, is this function continuous? Yes, no. Tell me about the limit from the left and the right. Tell me about, does the point exist? Are the things equal? Lots of them there to practice on. You got 30 of them. I suspect you'll get the hang of it before 30. Okay, so that's in section 1, 2. Average rate of change. Oh yeah, that was kind of easing us into derivatives. Average rate of change. That says if you have some data, let's say we have some times, and let's say the amount of snow. Go back to Montana. Okay, I don't know when the snow started falling. Okay, but let's say that this is 6 a.m., 8 a.m., 10 a.m., and noon. And the snow is in terms of inches. 3 feet's how many inches? 36 inches, isn't it? That's a whole yard of snow. Take a yardstick, hold it vertically, bing, that's how much snow they got in less than a day. Okay, let's say at 6 a.m. there was no snow. By 8 a.m. there was 4 inches. By 10 a.m., I'm making this up. Okay, so if you're thinking, where's he getting these numbers? I'm making them up. You're in a full-fledged blizzard. 30 inches, 2 p.m. Military time, what's 2 p.m. in military time? 1,400 hours, way to go. Okay, 36 inches. At 4 p.m., 1,600 hours, it's 36 inches. Hey, it looks like by 4 p.m. it stops snowing, doesn't it? Or somewhere earlier than that. Real fair question. What's the average rate of change? Okay. And let's say, first off, from 6 a.m. to, well, let's say 10 a.m. How would you do the average rate of change? It's real easy. It's a slope. Okay, average rate of change is a slope. Wait a minute, what slope? It's y2 minus y1 over x2 minus x1. That's it. You got to be kidding. That's all this is? Yeah, it's just a fancy way to ask you to do a slope. That's all this is. Okay, so is the time or the amount of snow the x value? Ooh, that's right. He may mix this stuff up on us. Okay, does the time decide how much snow there was, or does the amount of snow decide what time it is? Time decides snow, doesn't it? So the thing that's doing the deciding is going to be your x value, and then the other thing's got to be y. Aha! So between 6 a.m. and 10 a.m., I'm going to take the snowfall information at 10, so here's 18 inches at 10 o'clock. At 6 a.m., 0 inches at 6 o'clock. This is going to give you 18 over 4, which is going to give you about 4.5 inches per what? Hour, isn't it? While it is not true that the snow came down at a steady rate throughout that time frame, if you average things out, on average between 6 and 10 a.m., you're getting 4.5 inches an hour. Does that make sense? Okay. Does that make sense? sense how to do average rates of change? Average rates of change are important in business, in medicine, and various other applications. For example, in medicine, okay? Daniel takes a puck to the throat. Happens to him fairly routinely. And he's sore. He can't move. Takes some ibuprofen so he can keep playing. What does the concentration of that ibuprofen in his throat look like? Or actually in his bloodstream? Well, when you take up medication, isn't it absorbed, reaches a peak, and then over a period of time is filtered out of the bloodstream? Isn't that how medicines normally work? Okay. It would be very useful to know how quickly it's absorbed. That's called the onset time. Whoa, it's so important they gave it its own name. What's the average change in concentration over the first 15 minutes? Then the next question is, how long is this going to last? Is he going to need more before the third period of the game, or is he going to get through the whole game on 2 ibuprofen? Okay. The duration is how long is the medicine at a minimum effective level. Minimum effective level talks about what's the minimum amount needed in the bloodstream to provide relief from that pain. Does that make sense? To understand when you're going to hit this point of minimum effective level, you have to know how quickly it's decreasing, don't you? On average, how much is being filtered out each hour? Oh, that's an average rate of change. So that stuff you're reading on the back of the bottle where it says, for an adult, take 2 tablets no more than every 4 hours and no more than like 6 or 8 per 24 hours. Well, when it's talking about no more than every 4 hours, it's talking about looking at how quickly it's absorbed and how long a particular concentration remains in the bloodstream. What happens if you get the level up too high on Tylenol? He comes skating in, took a skate to the ankle. He's bleeding, you tape it up, and he wants to go back out and play, but it hurts badly. Can we just give him all the Tylenol it takes so that he feels no pain? Why not? Here, take the bottle. Here's your water bottle. Swallow that bottle of them. Chug down about a pint of water. What's the problem with giving him that much Tylenol? It'll poison him. It'll kill him. With Tylenol in particular, there is a maximum level that you cannot exceed. This is the lethal level. Oh dear. Do we want to be giving Daniel a lethal level of Tylenol? No way. I want him around for a long time. Love watching him play hockey and other things. So it's very important on medications to understand what is the average rate of absorption. How fast is this stuff being absorbed? Because that determines how much you can give at any one time. If you give too much, it's called malpractice. If you give too little, it does nothing. So what you're doing with the medication is you're kind of threading a needle. It's got to be in between those two. You see, average rate of change stuff is important. You may not see it directly in your face, but understand that there are lots of things that go on every day that affect you that are contingent on average rates of change. Okay? So that's section 1.3. In 1.4, we got into using the difference quotients. Oh, does anybody recall what the difference quotient is? Oh yeah, ooh, see this blue box here? Now featured in blue and red. That's talking about difference quotients, isn't it? You have a difference there, there's subtraction going on, and there's division. Oh, that's a quotient. Yeah, this is the stuff that leads into the derivatives. And then 1, 5, 1, 6, 1, 7. Get into different techniques for computing derivatives. One of the problems on the test is going to be several parts. It's just going to say compute the derivatives. Compute y prime. And it's going to give you y equals 3x squared minus 2 over x to the 5th plus the cube root of x to the 7th minus pi. So there might be one of them. Okay? Another one might be something like this. Y equals, let's say it's square root of x plus, let's see, we talked about the derivative of sine, cosine, tangent, and all that stuff, right? Okay, yeah, you don't want to admit it maybe, but yes, we did get around to that. And 1 over x minus pi plus, let's say 1 over 3x to the 7th. Even if you multiplied that out, is that going to leave you with terms that you can take the derivative of individually? It's going to leave you with a lot of little messes, isn't it? So how are you going to take the derivative of something like that? With lots of prayer, Chuck. It's a product rule, isn't it? Product rule. Here's F. Here's G. What's the product rule say? Y prime equals F prime G plus G prime F for FG prime. Yeah. Be sure you know that one. I will sell it to you on Friday, but it'll cost you about 3 or 4 points. Ooh, that's kind of expensive. It's easier to bring your own than to buy it there. Like going to the Reds game. It's cheaper to bring your own food than to buy it there. Okay? Bring your own product rules so you don't have to buy it there. Okay, another one, real fair game, would be something like this. Oh, maybe cosine of x plus 17x over, let's say 6x minus 4. How would you compute the derivative of that? Quotient rule. I am assuming that this question on the test Friday is going to be easy, quick points. Okay? See the first one there? You should be able to knock that off in maybe a minute or a minute and a half tops. Really? Yeah. That's 3x squared minus 2x to the negative 5th plus x to the 7/3 minus pi, right? You got to know your exponents. The derivative is going to be 6x plus 10x to the negative 6 plus 7/3 x to the 4/3. And I'm out of here because the derivative of pi is 0. How long did that take? The whole thing less than 20 seconds. That included rewriting it. And boom, 7 points. Almost a whole letter grade in 20 seconds. Yeah. Yeah, whoa, where are those, Chuck? This is looking interesting. Okay. On page 154 and 155, there are lots of questions. First off, stuff like this first question. Then, on page 155, starting with question number 57, it moves into compute the equation of the line tangent. Oh, wait a minute. How do you, with a tangent line, you need the slope and you need the intercept, don't you? That's a real fair question. Okay, we're going to be living off of that for the rest of the year, not just till December. Okay, so a real fair question is something like y equals 3x squared plus 4x plus 2. Compute the equation of the tangent line at, now I'm just trying to make something quick and easy here, x equals 1. Well, let's see, the equation of the tangent line is going to be y equals mx plus b, right? I need the slope. How do you get the slope? Everybody knows that. The slope is the derivative. Watch this. You've already got the derivative figured out, 6x plus 4, right? So the slope at x equals 1 is 6 times 1 plus 4 equals what? 10. So its equation is going to be y equals 10x plus b. Now, you got to be really careful. You were given an x value. We can plug that x value in right there, can't we? So we can rewrite this. This thing's just sliding all over the place today. As equals 10 times 1 plus b. On the left side, we're missing y. How do we get a value for y? Yeah. Notice this is labeled. It tells you right there y is. It tells you what y is, doesn't it? Oh, look, there it is. If I plug in x equals 1, we're going to get 3 times 1 squared. 4 times 1 plus 2 looks like about 9 to me. The y value is going to be 9. So this is going to give us 9 equals 10 plus b, where b equals -1. Does that look familiar? Hey, this one's done because we already have y equals 10x. What's b? -1. And there's your equation of the tangent line. Even with all the talking and stuff, that only took a couple of minutes. Once you get the hang of these things, okay, and that's the trick, and I am thrilled to hear, whoa, wait a minute, time out, Chuck, what page is this stuff on? I'm thrilled to hear that. I really am. Okay? I'm hoping that means you're going to go back and say, what's going on here? What I want you to see is, first off, can you do that derivative in seconds? Realistically? Yeah. If you can't, you need to head back to section 1.5 and get some more practice in. But I think for everybody here, you can write that derivative down in a couple of seconds. Does everybody know y equals mx plus b? Yeah. Can you plug in 1 to this derivative? Yeah. How long does that take? A couple of seconds. And boom, you've got the slope. Can you plug in 1 to the original equation? Yeah. How long does that take? A couple of seconds. Boom, you plug it in there. And then you solve for b. Well, you've been doing that since 7th grade. You've been working equations like that since 7th. I doubt that it was as far as 8th, but maybe 8th grade. Oh, that's another 8 points or so. Boom, boom, boom. Okay? Once you get the hang of this stuff, I mean, you can flat out fly through this. You can fly through this. Okay? People have asked me, Chuck, how do you know how much we can do in an hour? How do you make sure the test isn't too long? You want to know the truth? I can do the key in 2 to 3 minutes. That's how long this test takes, 2 to 3 minutes. Now, that's after you've been at it a while, okay? Am I expecting you to get this done? It's okay. It's not 2 to 3 minutes for you, okay? You've got an hour. Okay, but if you walk in having some understanding of this stuff, man, you can just pick off one thing right after another, can't you? Now, am I trying to intimidate you by saying 2 to 3 minutes? No. Okay. But I'm trying to encourage you to say, wow, you know what? Maybe I can speed this up a little bit. It's kind of like with driving. At first, it's 10 miles an hour. 10 miles an hour. You want to try speeding this up a little bit before we get rear-ended? Okay. And you're up to 25, and whoa, look there. Did you see that bush go by? Yeah, you want to speed it up a little bit? Well, that's what I'm doing. I'm sitting over there in the passenger seat saying, hey, you want to speed this up a little bit? Let's get moving here. Okay? And it's not because I'm trying to be mean or anything. I'm just trying to get you to improve. Okay? Make sense on the test? Now, I did not talk about any of the stuff in the review section. Well, I talked about the modeling in section R.7, but otherwise that's stuff that should look sort of familiar to you. And remember, can you get to a copy of the book on My Math Lab? Okay, it's there. The My Math Lab, it's there in My Math Lab. And when you look at it, the pages look exactly like this. Okay? Go to those sections, look at the homework, and take a look at them. You want the homework for section 1.6 as far as the pages? It starts on page 162. 1.6 starts on page 162. That's the thing I like about a book, man. You can just sport right through it and find the next section. Okay. 1.4 starts on page 144. While we're at it, 1.3 starts on page 133. That's kind of nice. 1.3, 133, 1.4, 144. Almost like a pattern there, right? Okay. 1.2, stuff about continuity. I think we already talked about that. It starts on page 124. That got them? Are you okay? I'm trying to encourage you. I don't want you coming into this class every day thinking, oh my gosh, calculus is bad, it's awful, it's horrible. It's whatever people have filled your brain with. Once you get the hang of this stuff, and I'm not going to say it's always going to be this easy. It's not. Enjoy this test. Really, dude? Enjoy it? Okay. Realize it can get more interesting. Realize that, wow, this is kind of fun. I can finish this problem in 15 seconds. Got it. Hey, what's one that's very likely to be on this test that we talked about at the end of class on Monday? Given y equals tangent of x, compute y prime. We did that the other day. You remember that one? Oh, yeah, that's just a quotient rule. It's a quotient rule with one sneaky, well, two sneaky moves, if you want to call it. Rewriting this as sine of x over cosine, right? That's the first move. It's kind of like chess. What's your first move? Rewrite it as sine and cosine. Now you've got a fraction, which means you're going to use which rule to compute the derivative? Begins with a Q. Quotient rule. Bless you. Quotient rule, huh? Hody high. Well, the derivative of sine is cosine. The denominator is cosine minus high. Derivative of the denominator. The derivative of cosine, be careful, is negative sine. That's the biggest problem people run into, over whatever's in the denominator squared. Does that look familiar? You're almost done at this point. You have cosine squared plus sine squared. Where'd that plus come from? Negative to negative over cosine squared. Is okay with that shorthand notation I'm using there? Now, here's where the trick comes in from back in your trig days. Oh yeah, we're supposed to have some kind of trig coming in here. Recall, cosine squared plus sine squared equals what? 1. That's right. So, this can be rewritten now as 1 over cosine squared, which is 1 over cosine times 1 over cosine. That's kind of a sad looking numerator there, which is secant of x times secant of x. How long did that one take? Way under 2 minutes. Okay. Now remember, off to the side here, just put some kind of little note. Attention, Chuck, here's what's going on. This is what allows me to go from here to there. That's what allows the substitution. Sine squared plus cosine squared equals 1. And this one's done. That's going to be worth about 8 points. No way. You're picking up almost a letter grade on each of these things, aren't you? And you can just click through them. Okay. That does mean you got to start studying before 6 a.m. on Friday. 5:55 doesn't count. Okay? You get the point. But I would encourage you to practice some more of the homework problems. If you get stuck on any particular section, there's a movie for every section, isn't there? They're all posted. All you got to do is go to Blackboard and look up that particular section. Really? I haven't used that, Chuck. I remember you mentioned it. Let's see here. I don't have it anywhere, so here we go. Let's just go with this. See, I really do use Wolfram Alpha. Canopy. Blackboard. Come on. The slowest part of this class is waiting for the computer to catch up. Log in. Go to the Meta Applied Calculus. Come over here, see where it says Course Notes. Boom. I don't know if you've been to this or not, but looky there. See all those little red lines? Okay. Those are notes. And the red line for each of these, oh, September 13th. It looks like I missed the movie there. It didn't load. But otherwise, do you see it? There's the movie for every class we've had up through Monday. Every single class is there. And all you got to do to get to one of them is click on it. And oh no, there it is. September 30. If you recall, on Friday, we were working on. Oh wow. Just started on a quotient rule. There it is. It's just that easy to get to any of these movies. Well, I don't want to see the whole thing. That's fine. Go to where you need to go. You know how to work YouTube. Okay? Does it make sense that there really is some support there for you? How late's the math lab open? Till 8 o'clock. They're open 8 to 8, 12 hours, Monday through Thursday. Friday night, don't study any calculus Friday. Take the evening off and celebrate the A you just earned. Okay on all that stuff? All right, we've got a couple minutes left here. Not going to let it go to waste. we're going to dive into the very last of the major moves or techniques for computing derivatives. This is going to be section 1.7. Is this going to be on the test? No, this will not be on the test. Okay, so in your notes, if you want, or what I used to do is test 1 ends here. Okay, that way I was never wondering and guessing, gosh, I wonder where I need to study up through. Okay, test 1 ends here. There it is. Last of the main rules. Then we're going to get into how do we use all this stuff. The last main rule that we're going to look at is the chain rule. This is kind of like unwrapping a Christmas present or a birthday present or something like that. Really? Okay, the way the chain rule works is suppose you have something like y equals the cube root of x squared minus 8x plus 7. That cube root's applied to the whole thing, isn't it? This can be rewritten as the x squared minus 8x plus 7 to the cube root's what is an exponent? It's a 1/3. That's kind of like a birthday present. The outside of it is the wrapping paper. Raising it to the 1/3 power is the wrapping paper. Okay? Now, when you unwrap a birthday present, Christmas present, whatever it is, do you rip everything all apart or do you take off the bow and the outside wrapping paper first? Yeah, usually that's the more appropriate way. Then after that's done, then you deal with the stuff inside, don't you? You open the box, you take out the plastic, the shrink wrap, whatever it is, and ta-da, there's whatever. These work the exact same way. What the chain rule says to do is you first do the derivative of the outside. Well, the outside is at 1/3 power. And if you want, let's see here, think of this green part is still being hidden. It's in the box. You can't see it. All we're dealing with now is the wrapping paper. So the derivative of that is going to be a 1/3 whatever is inside to the negative 2/3. Does that make sense? Where the 1/3 goes, where did the negative 2/3 come from? The 1/3 minus 1. Now, on the inside, guess what goes there? Well, in your present, when you're opening it and you've taken off the wrapping paper, did the stuff inside of the box change? No, it stayed the same, didn't it? So the stuff inside stays the same. Then, once you got the wrapping paper dealt with, in a separate step, you now deal with what's inside. In a separate step, you now deal with what is inside of the parentheses. That's all there is to chain rule. That's it. You gotta be kidding. It's gotta be harder than that, Chuck. This is calculus. This stuff's too easy. Sorry, it's all the harder it gets. We'll play with some more of these on Monday. Okay? This is section 1.7. Over the weekend, if you're thinking, gosh, I wonder, you can start messing around with some of the homework or looking at section 1.7. Okay? I'll see you Friday. I hope you have a great day.